Hello, everyone. Today we'll go over an introduction to energy and physics. Starting off, let's talk about the concept of work. Work, simply put, is the change of energy in the system. You can calculate it by the force times the distance. Next, kinetic energy is the kind of energy objects will have if they are moving. It is calculated by 1/2 mass times the velocity squared. So, for example, if you were to throw a ball, the ball will gain kinetic energy because it'll start moving. Now let's talk about potential energy. If an object has the potential to move, say because of gravity or Hooke's law if it's a spring, then it has potential energy. So for example, if you were to lift a ball up in the air, it would gain potential energy because when you release the ball, it'll start moving, falling to the ground due to gravity. Or if you compress a spring, it will move when you release it because of Hooke's law that will restore the spring to its natural state. So, objects will have potential energy when they have the potential to start moving because of forces like gravity or the spring force. Lastly, power is just the work divided by time. And what power tells us is how much energy is being converted in the system over the given time interval. So now we can talk about the law of conservation of energy. This law says that energy cannot be created or destroyed, only transformed. In more practical terms, it means that for problems related to energy, you can set the initial energy of the system equal to the final energy of the system. So the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. Then, if the object starts at rest but has potential energy, you can calculate how much that potential energy was transformed into kinetic energy by using this transformation of energy equation. We'll see this in the upcoming example, but first I should note that for these types of problems we can assume that there is no friction because friction converts kinetic energy into thermal energy, and we don't need to worry about that at this level. In future classes you may have to deal with that though. So let's look at an example. A 2 kilogram ball is dropped from a height of 5 meters. Assume there is no air resistance. What is the potential energy of the ball at a height of 5 meters, and what is the speed of the ball just before it hits the ground? So we can write down the initial energies. Since the ball starts at rest, it starts with 0 kinetic energy. And since it starts at a height, it will have gravitational potential energy equal to mgh. Putting in the values for the initial potential energy, we get it's equal to 2 kilograms times 9.81 meters a second squared times it by 5 meters. And this equals 98.1 joules. So, to answer the first part of this question, at a height of 5 meters, the ball has a potential energy of 98.1 joules. Now, let's solve the next part of the problem. We can lay out the conservation of energy equation, stating that the total initial energy is equal to the total final energy. Putting in the values for our energies that we know, we see that the initial energy is just equal to 98.1 joules, because the kinetic energy starts out at 0. When the ball is just about to hit the ground, we can assume it has a height of 0, or that there's no more height left since it's almost at the ground. Therefore, it has no more potential left. Thus, the final potential energy will be equal to 0. But the ball will still be moving just before it hits the ground, as all of the potential energy was converted into kinetic energy. So, we can set the initial energy of 98.1 joules equal to the final kinetic energy of 1/2 mass times velocity squared. Now, let us rearrange this formula to solve for velocity. So we get that velocity is equal to the square root of 2 times the initial energy divided by the mass. Plugging in the values, we get that the final velocity of the ball is equal to 9.9 meters a second just before it hits the ground.